Right. So today I want to do integration mainly, but I'm going to define the adjoint exterior derivative first. Just as something we'll put a pin on, and we'll come back to a little later. When we do Durand homology. And then I want to return to our story about integration. So we're going to define integration broadly. We're also going to define very specifically how to integrate over an object on the manifold, an object we call chain. And we're going to follow roughly the path that you followed when you first learned about integration. Okay. Obviously, we're going to generalize that, but that's basically going to be what we're going to be doing today. So, I left you off the last time with the following statement: that if I took one form, let's say omega, and I took another one form, eta, let's say in R3, then omega wedge eta is a 2 form. And the hot star of omega wedge eta is a 3 minus 2 to the 1 form. Another one. So if we interpreted the components of omega and eta as the components of vectors on 3, then star of omega wedge eta is nothing but the cross product. So this gave us an interpretation of what the cross product was, and we also understood this story where the metric dependence and orientation of the manifold enter. So this is kind of neat. I want to round up that example, so finish it up, by showing you similarly where the curve comes from. Right? So the curve, as the nabla operator across something, also has the same subtleties with definition in 3 dimensions. Right? So now we can understand where the curve comes from. So continuing with our example, I'm going to take again omega equal to omega x dx plus omega y dy plus omega z dz as a one form on R3. And I want to calculate what d omega is, the derivative of omega. So d omega would be acting on this one form. Right? I can only take y derivatives and z derivatives. So that will be something that looks like dy wedge dx and something that looks like dz wedge dx. Right? Yeah, I can take only x and z derivatives. Here, I can take only x and y derivatives. So, in doing this, I will find something that looks like dy wedge dx. And here, I will find something that looks like dy wedge dx. The only difference between them would be dx wedge dy. The only difference between them would be a minus sign. Similarly with the dz. So, let's do that and group all these terms. Then I will get dx, meaning d by dx. Of omega y minus dy of omega x dx wedge dy plus dz wedge omega y, sorry, dz of omega y minus dy of omega z d so that's d y wedge y and the z and the z and the y, and that's dy wedge dz plus and dz omega x minus dx omega z yes. And now I'll take the Now I'll take and my organization here is because of the question that you asked last time. It's not alphabetical, it's in positive permutation of x, y, z. So y, x, y, y, z, and z, x. But you can change them around as you wish. They'll just come at minus sign and there's a minus sign. There's a minus sign. And now I'll take the Hodge dual of this thing. The Hodge dual, remember, this acts on the basis forms. So the Hodge dual of x dx squared dy is dz. Hodge dual of dy dx is dx. That's why I'm organizing it in this direction. And the Hodge dual of dz dx is dy. So the output here is something that looks like dy omega z minus dz omega y dx plus dy wedge omega z, dz wedge omega x. Minus dx omega z dy plus dx omega y minus dy omega x dz. Okay, if we interpret omega as having the components that correspond to what we normally call a vector in R3, omega x, omega y, and z, given that this is a one form, the exterior derivative is a two form, and the Hodge dual of the exterior derivative is back again a one form. So its components can also be interpreted as components of vector. Which vector? Well, this is nothing but the curve of the original vector. Okay, now you can see where the curve comes from. Okay. Similarly, so this is the curve. This corresponds to similarly show that if you calculate starting off with omega being that star of omega. Omega is one form, this is an R3, star omega is going to be a two form, and it's going to be the two form that components omega x, that's x, so that's y which is z plus omega y t z which dx plus omega z dx which y. And now if I take the exterior derivative of this guy, this is just going to be d star omega. So star omega is going to be a two form, d star omega is going to be a three form. Which is three form? Well, yeah, I can only take one derivative, and that's the derivative with respect to x. Here the derivative with respect to y, here the derivative with respect to z. So this is dx omega x plus dy omega y plus dz omega z. This will give me a dx wedge dy wedge dz. That's fine. This will give me a dy wedge dz wedge dx. It's a cyclic permutation away from dx wedge dy wedge dz. And this here will give me a dy wedge dz wedge dy wedge d instead wedge dx wedge dy, which is again a cyclic permutation away from x, y, z. Okay. So overall, I can pull this out, leaving me with dx wedge dy wedge dz. That's the B form. It's the highest form you're going to get in R3. And now if I take it again, a hot star, or only actually this guy, so this hot star, the three form is one. That's just the function given by which function? Well, this is just the divergence of the vector. This last example is actually a little bit instructive. This here is a zero form, it's a function. And it's a zero form that I got by taking a particular combination. I took star, D star, acting on a one form. So this combination, that's a one form, lives in omega one, to a zero form, or something that lives in the set of functions over M. And in fact, this is a much more general statement. This is a statement that more generally in the following sequence. If I start off with an R form on M, and I act with the object star operator, if the dimension of M is little m, then this takes me to an M minus R form on M. Then if I act with the exterior derivative, this takes me to an M minus R plus 1 form on M. And then I start this again. And this takes me to an M minus R plus 1, which is an R minus 1 form. R minus 1 form. Okay. In other words, the combination of star D star again takes me between the set of R forms and the set of R minus 1. In the same way that D, the exterior derivative operator, takes me between the set of R forms and the set of R plus 1. So if the exterior derivative operator increases the degree of the form by 1, the combination star D star decreases the degree of the form by 1. In fact, this allows us to define the so-called adjoint exterior derivative denoted by d dagger, and d dagger is equal to d dagger maps omega r to omega r minus 1. And d dagger is minus 1 the m r plus m plus 1 and star the star. This minus 1 nonsense in front of it is to keep the counting to come out right. So this is actually an adjoint operator with respect to some inner product, right? So you know how adjoints work effectively by integration by parts. If I define some inner product, then what we'll find is that the inner product between some form and the exterior derivative of another form is the same as the adjoint exterior derivative in the first form in product with the second. Okay, and for that to come out correct with the integration method that we use, we need this minus 1 to the r plus m plus 1. And as we would suspect, if we're dealing with a Lorentzian manifold with an indefinite signature, then this number here will change, but we don't need to worry about it. The point is, this -1 to the something is there to make sure that this guy is an actual inner product. It's an actual adjoint defined with respect to an inner product. I will come back to what that inner product between forms looks like, because we're going to need it when we talk about Durand homology. But for the moment, I need to note that this guy is also a nilpotent. Okay, so I said every time you see a nilpotent operator, something squares to 0, you should go hunting around for structure of homology or cohomology. Okay, so this guy is the note that d dagger squared is star d star d star. Star squared is proportional to the identity up to some minus sign, but we don't really care about that. The point is that this guy is proportional to star squared star. The 0 because d is 1. Okay. Okay. So now let's return to our original goal, which was integration on manifolds. And I want to start by defining for you the integration of a function on a manifold. So suppose I have some function f that has the manifold R. This is some real value function on the manifold, and I'm assuming that n is an oriented to a manifold. So I can actually do integration on the manifold. And I'm going to assume that vol of M is the volume element on M. So now I'm going to define the integral of F times volume on M over some local coordinate neighborhood UI with coordinate X. So the local neighborhood of some point P with coordinates X on P. So this is a function times the volume form on M, right? In flat space, this would be in flat, let's say, n-dimensional space, this would be F times dx1, dx2, dx3, etc. Well, actually, dx1 wedge dx2 all the way through to where dx. So my definition then is to relate this thing to an ordinary n-dimensional integral of a multivariable function. So this guy I know I can write as phi on ui. This is the map that takes this coordinate neighborhood to the associated open setting R to the n. And this is S of phi inverse on X, H of phi inverse of X, dx1, dx2, dx. So you remember the volume form was defined up to some strictly positive function h, and that's the function that I'm interested in. Now, given that the volume form is defined up to some positive function, you might wonder why is it that I'm not just choosing h1? Just choose the volume form, just dtx1 is it? Well, the reason is because in the transition between the UIs, it's not this h will pick up the fact that the Jacobian transformation between those the coordinate neighborhoods. And so what's one in one coordinate neighborhood is not necessarily one in another coordinate neighborhood. So I'm going to keep these guys around for as long as I need to. And then when we do specific examples, you'll see where it features. The point I want to make here is that on the left-hand side, we have an integral carried out over the manifold M. On the right-hand side, we have a usual m-dimensional integral carried out over flat space. Okay, so this is the m-fold integral that you already know and love from second year. This is something new. This is an integral over the manifold. And the manifold could be curved, could be however many dimensions you want, it doesn't really matter. Okay. Yeah.
So is that just pretty forward on n-fold m, but like 5 and 1 on the right hand side?
Yes, that's right. Okay. So keeping in mind the rest of the map from M to R, just follow that map, which allow me to define S on R to the end. So that's what that is. So the point here is that the left-hand side is an integral on UI, some subset of M. The right-hand side is an integral on the M. So this is the usual integral that you can already know. One caveat is that this integral is defined on a subset of on a local subset of M. Right? So now I need to tell you how to integrate over the whole of M. Right? So what we did in deciding how to describe M in the first place was we took all these local coordinate neighborhoods and then we do them together with transition functions. Right? So now what I've done is I've shown you how to integrate a function over one of those coordinate factors by adding it to push forward to an integral over M. So an ordinary M-fold integral on flat space. I need one more thing in order to be able to extend the integral over the whole of it. And that one more thing is what we call the coefficient of unity. So to extend the integral over all of M. We need a position and as the name would imply, some way of breaking up one that allows us to do integrals over different patterns that overlap by transitioning smoothly between them. Okay, so let me tell you what coefficient of unity is. So suppose I have some collection of charts UI, some set of UI. I have some set of UI as an open covering of some manifold M. And I'm going to assume that each point of M is covered by a finite number of UIs. When I can always do this, the manifold M is called paracompact. So, I might have mentioned what paracompact was. We needed manifolds to be paracompact at Hausdorff, so this is one reason why we needed to be paracompact. Okay, so here's the story. So if a set of UI are is an open covering of M such that each point in M is covered by a finite number covered by a finite number of UIs. Okay, phrase that. So let UI be an open covering of M such that each point in M is covered by a finite number of UI. Then parenthetical statement here is that this is always possible if manifold M is compact. I'm going to assume that all manifolds that we'll be working with satisfy this. Then a partition of unity is a family of differential functions epsilon I. Epsilon I. E. That satisfy the following three conditions. One, that these epsilons lie between 0 and 1 each time. Two, that epsilon I of P vanishes when P is not in UI. Outside of that coordinate chart, outside of that coordinate chart, epsilon I vanishes. And then finally, that the sum over I of epsilon I of P equals 0, equals 1, and it's a partition of unity for all points P. And this is what we need for compactness, is in a paracompact manifold, this sum is finite. If we can find some partition of unity, actually technically it's called a partition of unity subordinate to the set UI. In other words, partition of unity is how you define a partition of unity depends on your coordinate chart, your atlas. If we can find such a partition of unity, then we can write our function s right away. then the following is true. My function s of p is the sum over I of f of p times epsilon I p, because for every p I can break up one in that way. And then I can use this to define sum over I of f I. So this is note if m is compact, this will finite range. That is if p not m beyond. And then finally, I can now put all this together and write then that the integral over m of f of m, in other words, the integral of this function over the n-dimensional manifold m, it's sum over I of the integral over each of the ui of f I and each of these guys I can calculate by mapping it to flat and dimensional space part of the n. So then I do the usual integrals that I'm familiar with, and then sum over all of the I, and that will give you the integral over the integral of the function. One point to keep in mind is that a different atlas, a different choice of the UIs, will give you a different set of coordinates and a different partition of unit. But at the end of the day, that integral will come out to be the same. You're very welcome to check that. Okay, so let me do an example of how this works. Let me say at the outset, I'm not claiming that this way of calculating the integral is the most efficient way of calculating the integral. Yeah.
So when you define the integral, so if you go up, is it possible for the integral to be infinity?
It's possible for the integral to be infinity. I realize this as soon as I wrote it down. It's not that the sum is finite, it's that the sum ranges over a finite number.
You know, on the problem, say with like something over integral, which could be infinitized.
Yes, yes, the integral can certainly be. Yeah. And integral like this is not infinite, then quantizing gravity is kind of trivial as well. So part of the problem here is that we can calculate these things over m and sometimes get divergence. So I'm not saying anything about the divergence problem. The integral is defined. So let me do an example to illustrate how this works, and I want to calculate something that whose answer we already know, and it's calculatable by elementary methods in a much easier way. But I want to illustrate the point of the partition of unity. Okay, so suppose I want to calculate the integral of I to the integral over f1, the unit circle of omega, where omega is cos squared theta. The volume form on the unit circle is just d theta. Okay, as you go around the unit circle. and I want to integrate this function, f theta equal to cos squared of theta. Right? So obviously, the integral from 0 to pi of the whole circle of cos squared theta d theta is pi, right? Everybody knows first order. But let's see how we would pick a particular unity and do the integral that way. So I'll start by writing down charts that cover the circle. U1 is f1 minus 0.10. So you take the circle, you eliminate the point along the x-axis at 1, and U2 will be circle minus point minus 1, 0. It's diametrically opposite. And you can show that if this is the S1, then these two charts, the yellow one, starting here, eliminating this point, and the red one, starting here, cover the circle. Right? So this is U1 and U2, and I'm very specific, we do not include that point and that one. And the union of these two charts will cover the circle. Okay. The charts. This one. I believe we can check that it satisfies the properties that we require, but a partition of unity is given by epsilon 1 of theta equal to sine squared over 2 and epsilon 2 of theta equal to cos squared of theta over 2. So leave this to you guys to check. We check by showing that epsilon 1 and epsilon 2 satisfy these properties. Obviously, it lies between 0 and 1 in sine squared and cosine squared. You can check also that epsilon 1 is 0 if point P is not U1 at that point, and epsilon 2 is 0 at that point. You can pick, well, it's obvious the model that sine squared plus cos squared. So what this means for us doing the integral is that, and this is a particular opportunity subordinate to the charts U1 and U2 that we picked. Pick the charts, also a good exercise, and a different particular unity, and you can show that this must hold as well. So then our integral, the integral over S1 of cos squared theta d theta breaks up into an integral over U1. U1 will go from 0 to pi, sine squared theta over 2 d theta plus cos squared theta theta plus integral from minus pi from there of cos squared theta over 2 cos squared theta d theta. This integral is pi over 2. This integral is pi over 2. Check this. And so the result is, as we would expect, pi. Okay. When you first learned about integration, what you had was an interpretation of the integral as the area under the curve. So I gave you some curves like this. I said calculate what is the integral from a to b of this function f of x dx. So what you did there, not calculate areas, is you took this integral, broke it up into pieces, such that on each of these pieces, you have polygon. The area, you know how to calculate it as polygon. That gave you an approximation of the area under the curve. The area under the curve being the integral. Okay. So the upshot here was that the integral, or the integral from a to b of this function f of x dx, or as we now say, the integral is one form over this one chain. And then we have defined chains here, the defined line was approximately the sum of the area of polygons. Okay, all the polygons, and then you made this integral exact by taking an infinite refinement of that splitting up into polygons. Okay, so that's what you did in first. The question is there a generalization of this to what we're talking about with manifolds? The answer is yes. And to do that, I need to generalize the idea of a polygon to an arbitrary space. The generalization of the idea of a polygon to an arbitrary space is what we call a simplex. There's a whole lecture course talking about simplexes and there's additional complexes, and this will lead onto some beautiful mathematics. This is essentially the essence of differential topology. And I would love to go there, but I don't have time. So what I'm going to do is I'm going to tell you about the simplexes that we need to define this integral, and then we'll talk about the round homology of this set of objects. And if anybody wants, maybe at a later stage, I can give us a course on differential topology. It's something that I'm currently quite interested in because it has application to the idea of topological data analysis. If I have to do in the audience topological data analysis, you guys are system homology. So this is the idea that homology, state of things, depend on how closely you look at them. And certain shapes appear, disappear. You look further or closer to points on a map. But you can do really cool things with persistent homology in data analysis. A whole branch of mathematics called computational topology, which is super interesting and something that I'm quite excited about by now. But for the moment, I want to focus on a particular class of perspective that will allow us to generalize this argument. So the generalization of the polyhedra polygons is what's called a simplex. So a simplex is a generalization of I don't know. So what I want to do here is essentially the same strategy that you guys, in fact, I'm not gonna just take this last bit and then we can stop and then I'll pick that up on Wednesday. Right? But, the strategy I'm going to use to define an integral is going to be similar to the strategy that we used here. So I'm going to take the integral of something over this manifold. We've already defined how you integrate functions, but we want to integrate forms. Right? And I'm going to break it up into basically flat pieces. And then essentially use a pullback operation to relate this to integrals over the flat pieces. So it's the same thing that you kind of did here, right? When you calculated the area of the polygons, because you know how to calculate the area of the polygon because it's flat. Whereas this guy is curved in some way that you didn't understand at first. Okay? But you know how to calculate these guys of base times height, whatever base times height. You know how to calculate those. And so what you did was you mapped the area under the curve or the integral to this approximate thing here that you calculated, and then you just made the polygons thinner and thinner and thinner. That was the refinement of your calculation of this area, and that gave you the integral in the limit. Okay, so we want to do something similar. We want to take an integral of form over some object. That object is going to be the image of a flat simplex on the manifold, and we're going to define that integral by relating it to the integral over the simplex. All of the simplices are flat, so they're going to be normal n-fold integration of the or r-fold integration for an r. And then we're going to build packs from there, show how to calculate this over. Maybe I have time to just define. Okay, let me just define this. So simplex is a generalization of the polygons that we're already familiar with. And if we denote points in R to the R, so denoting points in R to the R, by these are not any other point, these are specific points by E naught will be the origin. E1 will be the point along equivalent of the x-axis. E2 one along the y-axis, that got all the way through to PR. We have one in the R position. This, then the standard R simplex sigma R bar is the collection P naught P1 PR in R with the R and lines joining them. So essentially is sigma R bar is the set of all points x1, x2, xr in R to the R such that x mu is greater than or equal to 0, and the sum over mu equals to 1 to r of x mu's are less than or equal to 1. Where the x mu is the coordinate on r to the r. So for example, in R2, the standard simplex x and y, and the standard simplex is triangle that joins E0, E1, and E2. That's 2 bar. And in 3 dimensions, pyramid, third, that's this. 1, 2, 3, this is 8. Okay, so I will pick up again on Wednesday and tell you how we then define integration over manifold by mapping the manifold into these R13. And then doing the integral of the form over the flat R. And this will lead us directly to the idea of chains, boundaries, and cycles, which will then lead us to their own cohomology.